They use a lot of the same stuff, a lot of the same mathematics that we saw earlier. Not all of it, rather, but at least the stuff I want to kind of emphasize to you guys. Let's get there. 9, 11, 27, and let's take it from there. So on this one, you guys, number 9, the near point of a person's eye is 60 centimeters. To see objects clearly at a distance of 25 degrees at 25 centimeters, what should be A, the focal length, B, the power of the appropriate corrective lens? Neglect the distance from the lens to the eye. Okay, so we're talking about the eye here and some of the stuff that we have. Let me get through these problems for you guys, because the time constraints are pretty significant right now as we're here. I mean, there's going to be next to nobody at this campus tomorrow. So let me get through this. I got to get to another class as well. So let's see what we can say about all this. All right, guys, the near point of a person's eye is 60 centimeters. That's the best they can see without glasses. To see objects clearly at a distance of 25 centimeters, what should be the focal length and power of the appropriate corrective lenses? Okay, so for this right here, you guys, we're coming right back. We're coming right back to the stuff we did last time, which is kind of neat in its own right. That's visible, Christian, isn't it? Is it the that's okay? Okay. I told you we'd see this stuff again, or at least I kind of implied that we would, right? We talked about it for we talked about it for mirrors. So we got this. P This is interesting. Let's talk about this. This is going to be a virtual upright image. If it's a virtual upright image, it's as though we see it somewhere in front of us. So it should be a positive 60 if it was behind us, but since it's in front of us, it's a negative 60. You want to be able to see, you want to be able to form an image where the near point is. The near point for the person is 60 centimeters. That's the best they can see. Well, okay, let's bring that thing to 60 centimeters away from us. Okay, it's going to be virtual. It's going to be a virtual upright image, so we'll call it negative 60 centimeters. And the object is 25 centimeters away. You want the image to be where your near point is. You want to bring the image to where your near point is, and the object is 25. So there you go. You're doing this, and let's see what's going to do it. A number of ways you can do it. 1 over f. Again, guys, we are talking about, notice the stuff is here to stay. I mean, you got this. That's what we had. Let's deal with it. 1 over f. 1 over object distance. So that's the object distance. Let me actually just write it like this, just for now. And you can go about it. You can solve it any way you want on this. Let me just we can identify this stuff pretty good. 25 centimeters is the object distance. The image distance is this. And just do what you got to do. I mean, we've been down this road before. The way this ended up turning out, remember when we did some of the stuff, you saw me do the wheeling and dealing with the mathematics on this stuff earlier. How we're actually going to get there to get it. For this right here, you can make, multiply it for this item right here multiplied by a special 1, Q over Q. Here for this item multiplied by a special 1, P over P. And then after all is said and done, it's PQ over, as we said here, it's going to be Q plus P. So what happened here? So the F is going to be, let's see what we got. We got 25 times negative 60. And on the bottom here, we got negative 60 plus 25. This right here, negative 1,500, I think. We'll have to kind of look at it. I think it is. Negative 1,500 right here. Add these right here. That's negative 35. There's so many ways to do it. I did it, in my notes I did it a little differently, but we should be getting the answer correct. Go right here, negative divided by negative is positive. I'm just trying to look at this thing. Yeah, it's gonna be 300 over, it's gonna be 300 over 7. It comes out back to 300 over 7 centimeters. That is, I did it a little differently in the notes, no big deal. .42.9 centimeters is the focal length. That's 0.429 meters. The same thing. I mean, it's just different units, right? And as far as that's A. As far as B is concerned, the power in diopters is simply 1 over F in meters. 1 over F in meters. So it's 1 over 0.429, just by definition. They call them diopters. It's inverse meters. And what happens at the end of all that? You get 2.33 diopters. So 2.33 diopters. They call them diopters. 1 over, but it's got to be in meters. Remember, it's got to be in meters. And then at the end of it, it's just the unit, the inverse meters, they call them diopters for these circumstances right here. So that's it. I mean, that ends the whole story on that one, you guys. Is that pretty legible, or should I write it somewhere else? Pretty good, okay. So there it is. 2.33 diopters on that, and that's number 7. Number 11. Number 11 is saying the accommodation limits for nearsighted Nick's eyes are 18 centimeters and 80 centimeters. When he wears glasses, he is able to see faraway objects clearly. At what minimum distance is he able to see? At what minimum distance is he able to see objects clearly? So, the accommodation limits for nearsighted Nick's eyes are 18 centimeters and 80 centimeters. When he wears his glasses, he is able to see faraway objects clearly. At what minimum distance is he able to see these objects? So when they talk about these accommodation limits, guys, what they're trying to say is, let me kind of read from the key on this one. For problem number 11, we are told his lens must form an upright virtual image of a very distant object at his far point, 80 centimeters in front of his eye. So in other words, he sees things well at 18 centimeters away from him, and from a distance, at a maximum distance, he sees things well at 80 centimeters. So the maximum distance at which he sees things well is 80 centimeters. The maximum faraway distance at which he can see things well is 80 centimeters away from his eyes, and he sees things close at 18 centimeters from his eyes. So his lens must form an upright virtual image of a very distant object, P almost infinity, at his far point, 80 centimeters in front of the eye. So let's see what he can do on this. They gave us the information that they gave us. Let's see what we can say about it. So again, I got this in the notes as well, you guys. His lens must form a virtual image of a very distant object. So P, if an object is very distant, he's got to be able to see it. Almost infinity. If it's almost infinitely far away, he's got to be able to form, it's got to be able to form, his lens must form an upright virtual image of a very distant object at his far point, 80 centimeters in front of the eye. So the image has to occur at 80 centimeters in front of his eyes. So let's see what we can say here. So what they're saying here, what are they talking about? Well, they're saying at this point, what kind of focal length are we talking about to get this done? We got to say 1 over f is equal to 1 over something very large. And I think I maybe even written it that way when I did it. Infinity, or close to it, very great distance. Yeah, infinitely far away, and he's got to be able to bring that object, or close to it, very, very far away. He wants to bring it to his near point. Bring it to his far point. And so if that's the case, you guys, it's got to be an upright virtual image. So let's see what we can say here. At his far point in front of the eye. So it's got to be, his lens must form an upright virtual image of a very distant object at his far point, 80 centimeters in front of the eye. Well, if it's in front of the eye, the image, that's not where we wanted to project the image. It's got to be in front of the eye. So and that's a negative. 1 over a very great distance is practically 0. Get the reciprocal of both. So we've got this. The focal length is this for the far point. Now we need a virtual image at his near point. So for the near point, you guys, you're essentially saying, we've got the focal length there. So let's see exactly where, I think the way they asked the question, let me just ask the question one more time. At what minimum distance is he able to see objects clearly? Okay, with the correction that has taken place, let's see, given the correction that has taken place, what's going to happen? Well, we're talking about again, virtual image, so it's going to be a negative sign in there, guys, when we're doing this stuff. F is going to be tell you what I'm going to do. Let's just do what we usually do. Let's find out the object distance. What's the object distance? Where can this all happen? Given what we've already determined for the focal length. The focal length stayed. They're the same glasses. We're not throwing the glasses away. The focal length that we determined is what we're going to use. The image you know, we want the image to be at 18. The problem is, with it being at 18, the images are all going to be in front of us. These are all going to be virtual images. If they're all virtual images, the numbers associated with them are negative. The Q that was associated with the 80 centimeter distance, because it's a virtual image, it's on the wrong side of the lens, or actually it's on the right side of the lens for us to see it. But if it's on that side of the lens, for it to be virtual, it's got to be a negative. Same thing here. These got to be negative. This plays out as solve for 1 over p. One over p equals 1 over f minus 1 over q. Man, you're calling this one. I mean, we can do a whole bunch of things here. Flip them, you know. 1 over p is this. F times q, you know, do a special one, q over q, special one, f over f. F times q, here's q. F times q here, that's f. This doesn't have to be, I mean, I don't know, maybe I'm not even looking at how I did it in the notes, guys, but it doesn't matter much. Do the mathematics that you feel most comfortable doing. Just make sure you're doing the right mathematics. The math is the math. It's going to be right. F is negative 80. Let me see here. F is negative 80. Q is negative 18. Let's see here. F is negative 80. Q is negative 18. And let's do it again. Q is negative 18. F is negative 80. Now be careful here. Really careful. Multiply these two. I'm just going cold here. Negative times negative is going to be 144, negative 1440, I think, when we do this. Yeah, let's actually kind of just look at it a little bit. Yeah, that should be right. I mean, when we're looking at something like this, 72, 144, yeah, I think it's about right. Go here, and you get 62. So we got that. The end of the day on all of that, you got negative 23.23. Again, check my math, guys. I'm really in a hurry, and we are kind of, I know everybody is, we're all in kind of bad times right now, but I think the math is on. I mean, and this is, it looks about right. I mean, if you were to take this and multiply it with 62, you should get the negative. The negative 23.23 multiplied by 62 should get you in the ballpark of negative 1440. So there it is. So they're saying that's, for some reason here, I'm thinking, why on earth is it not, forgive me, guys. This should have been, negative times negative is positive. I got the right absolute value, so it's positive divided by positive. Straight out, give me that. Well, what does that mean? Well, I mean, you can put the thing a little further away from him and he can still see okay. You can put it at 23.23 centimeters and he can see it at the 18 centimeter near point that he has. You can form an image there at the 18 centimeter near point regarding all that. So that's what we said there, guys. That's number 9. That's number 11, rather, I'm sorry. 9 is the far one over there, and that's 9, and this is 11. So, looking good. Let's go to 27. 27, it should go pretty straightforward, guys. The compound microscope and the telescope. The desired overall magnification of a compound microscope is 140 times the size of what you originally had. The objective alone produces a lateral magnification of 12. Determine the required focal length of the eyepiece for that to happen. They are both working together, guys. You're going to work with the objective with the objective and with the eyepiece. So if you multiply the two magnifications together, you'll get the grand total magnification. Magnification capital M equals M1 plus M2. I'm sorry, magnification capital M equals capital M1 times capital M2. Okay, so let's get to that. Let me erase this and we'll take it from there. Okay, pretty straightforward here with that one, guys. How do you get the 140 magnification? We got two things helping you out there. So we'll take a look at that. Pretty straightforward. There's the eyepiece, there's the magnification. They're trying to tell you basically on this. Got to be careful here. What they're saying is the 25. There's something here I think I need to mention really quickly. There's a lot here that I need to mention. I don't know how much time I got. If you go to page 832. The overall magnification on the bottom, the compound microscope. The overall magnification of a compound microscope of length capital L. The overall magnification of a compound microscope of length capital L is the product of the magnification produced by the objective or focal length of focal length FO and the magnification produced by the eyepiece of focal length FE. There is actually go in, they get into this a little bit, they talk about this. The angular magnification of a lens is defined as m equals theta over theta at 0, where theta is the angle subtended by an object at the eye with the lens in use, and theta 0 is the angle subtended by the object which is placed at the near point of the eye and no lens is used. The maximum angular magnification of a lens is max is 1 plus 25 over f when the eye is relaxed. The angular magnification is 25 over f. So they're saying basically when you're talking about doing the magnification up close like that, the distance that they try to put it at is 25 centimeters. That's the ideal. It's not going to work beyond that. And they show some stuff regarding that. So let me write this thing out, you guys. I'm not entirely pleased on how they write some of this stuff, but the discussion of it's not that good. But I can tell you for sure this works for this exact kind of problem. And at this point, we might have to just leave it at that, given our time constraints. Let me try to be as reasonable as I can be when we are doing all this stuff, I guess. I just told you that the grand total magnification M is going to be magnification 1 times magnification E. So they're telling you different things here that can happen. So saying, so for the eyepiece itself, you guys, they're saying the magnification for the eyepiece I don't know this, but the eyepiece is going to be 25 centimeters, 0.25 meters, in the focal length of the eyepiece. So, and what they're saying here is, it is, for this particular case, how are you actually going to do this? Find the focal length of the eyepiece that's going to make this all happen. So what we're going to say here is, let's multiply by FE on each side. Multiply by FE and divide by small m. And divide by small m, and you got this guy's just 25 or just 25 over 1, just to kind of keep the record straight. The focal length of the eyepiece is going to make it happen is, we are told, so wait, let me just read it back here, man. This is the overall, the desired overall magnification, that's that small m. The desired overall magnification of a compound microscope is 140. The objective alone produces a lateral magnification of 12 times. Determine the required focal length of the eyepiece. So you want the objective that we look at, you guys, by itself. So we got this right here. So let me kind of write that out. The objective alone produces a lateral magnification of 12. So the objective, guys, for 12, that'd be the big one. You want the grand total to be 400. I'm sorry, 140 rather. And this is just 25. When you grind this out, guys, the eyepiece, it's going to be, again, I'm not thrilled by the discussion that they gave pertaining to this. If it, you know, if I, that's how it's working there, guys. What they're actually calling what, the way this thing plays out. You know, what would the magnification of the eyepiece be? I've seen this discussed in different ways in different books. I think better than this, to be honest with you, than the way they're actually, this is the one place I'm not entirely very comfortable with the way they're discussing some of this. But, you know, the way they bring the thing here, guys, they're looking at it here. The overall magnification of the compound microscope is defined as the product of the lateral and angular magnifications. The negative sign indicates that the image is inverted with respect to the object. The microscope has extended our vision to previously unknown realm of incredibly small things, and capabilities of this instrument have increased steadily with improved techniques and precision grinding of lenses, guys. So, the way they want to look at it, I mean, it's just that the drawing of it is not, I'm trying to see it as best I can. There's the objective, there's the eyepiece. The eyepiece is what you're encountering, and the eyepiece lens forms an image here, and how that actually comes about. So you're finding, you know, you get pretty good discussion of it on page 821. I'm not going to greatly emphasize this particular problem like this moving forward. Let me look at it as we go. If there is any question of it, it'll probably stay just at this level, you guys. Pages 821, 822, especially the middle of page 822, and so on and so forth on that. Probably won't go much more on that, guys. I'm obviously, I can't, there's a lot of limitations here on what I can do and what I'm able to say on this. It'll probably stay very, very close to a problem like number 27 if you do get asked beyond what I did right now. Okay. That will be it for Physics 122, you guys. This is not going to be greatly emphasized. Be able to do it in the way that I just showed you this right here, looking at those pages 821, 822, probably just at this level. There's a lot more we'd like to do and like to ask. I'm not entirely, I've seen other books handle this subject matter a little bit better, I think, if I'm recalling correctly. But anyway, it is what it is. That is it. All the best to you guys. I want to thank Christian for all his hard work here. We are maybe one of about 10 people on campus right now, so it's like a science fiction movie, you guys. So do well, hang in there. Let's get through this. You know what's going to happen with the curves. Because this is harder, if it's going to be harder because of what's going on with us, you know, that should be manifest in the curve. The curve might come lower too. So if it does, nobody's looking to create problems for anybody, guys. We're trying to get through this. This is something that you hopefully live through never again. It's kind of like one of those once in a lifetime things. I've never seen this in all my years, so let's just do what we can do. Okay? Thank you much. Stay safe. Okay?